Yep. All right. Good morning, everyone. Thanks for coming for the session, and thanks for the wonderful attendance online. Right now, about 250 people are online. Well, about, I don't know how many folks here, about 50 odd are going to be in the room. I am Sayan Pathak, and I am part of the CNTK team. I'll walk you through this tutorial. I would like to acknowledge Frank Saida here. He's in the blue shirt. He is the architect for CNTK, and I have borrowed a lot of the content from him. I've learned a lot from him over the months that I have been with the team, and he's here to help out with any difficult questions you may pose. I would like to also acknowledge Amit Agarwal, who is also a co-architect for the V2 version that has come out, and a lot of the content coming from him is also incorporated in this slide. So before we get started, I'd like to get an idea of how many of you are new to machine learning. Fantastic. I can't see the folks online, so this is good. You have an idea of machine learning. How many of you are new to deep learning? Okay, fantastic. And how many of you have done some deep learning training or played around, built models using any of the toolkits? Okay, brilliant. Not being able to see folks online, it's a bit challenging for me to assess the crowd, but taking this as a decent sample, I can say that there are folks in the room of various levels of expertise. So I'm going to start at a very high level today, like from the stratosphere maybe, and slowly descend down to see the landscape, and then we will hit the ground. And as we hit the ground, I expect some of you to be driving an automated car, which is pre-cooked in the form of the tutorials. And then some of you will probably try to pull the engine open, replace the 2-cylinder engine with the 4-one. You may want to get rid of the engine and see if it can be run without that. So things like that. To just give you an idea, today morning as I woke up, I got several mails from people who are attending who actually want to do that, who have posed me different questions regarding the guts of CNTK. So I really appreciate those questions. Please keep those questions flowing in through Skype. Somebody's taking a note of that, and I will get to every one of them. So today's agenda is an hour of talk about what CNTK is, starting with a very high level. That'll probably go for about 20 to 30 minutes. Then we'll go into a little bit of nitty-gritty of how CNTK, what are the features of CNTK and how it may compare against other deep learning toolkits. And then in the second and the third hour, we'll get into dealing with the tutorials. The first set of tutorials are going to be elementary ones for many of you who haven't been familiar with deep learning, should be able to run those and get a feel for it. And the ones later on are more advanced ones. For that, we will see how much there's an appetite. I'll take a poll towards the second hour to see what you guys may want in the room. And folks online, just tag along. This is a broadcast session, and we will try to get to your questions as fast and as many of them as I can. Okay, now if this clicker can work. All right. Okay. Which one? Oh, I see, I see. Okay. So what's Microsoft Cognitive Toolkit? So the toolkit is designed around ease of use, focusing on a problem that your user needs to solve without having to worry about the guts of it. So many of you who want to try the toolkit, you'll find that condition being very appealing. So the idea is that you focus on what and not the how. However, if you want to get to the hows, the source, the toolkit is completely open source. So you definitely can get into that. So the toolkit prides itself in being the best in terms of speed and scalability. And hopefully towards the end of my presentation, you'll be convinced that the features that we have built in are what makes the toolkit really performant on very large scale production data. And it's flexible, so you'll see that various components can be put together in a very easily composable way. And as you are taking that tutorial, as you're working through the examples, I'll point out areas where you can go and then explore refinements to your code to see what do those Lego blocks when they are swapped out in and out mean. These are both supported for Linux and Windows. We treat them as first-class citizens. And it's a fully open development frameworks. All our development is in the open. There is no internal version. So if you go to our GitHub site, you can find every which branch that people work on CNTK is out there. For people in the room, this is a tutorial hands-on session, so please feel free to interrupt me. And for people online, send us the question. We'll tackle them as we go along. Is this the one? I was having the wrong clicker all the time. All right. That makes it a lot easier now. Or maybe not. Okay. All right, cool. So I want to start off at a high level for where else this toolkit is currently being used. So Microsoft Cognitive Services. How many of you have heard about Microsoft Cognitive Services? Great. So many of you may be already aware of all the different functionalities the toolkit provides to power different use cases made possible through the Microsoft Cognitive Services in speech, vision, and text-based deep learning applications. Microsoft's customer service bot, this face detection framework are to name a few. Now, machine translation is a very rich bed for deep learning applications that the company leverages for facilitating various experience on the Skype translator. Cortana learns acoustic model using CNTK for scalable training on very large data sets. So I'll keep repeating very large data sets because you'll realize that as we get into deep learning, you do need the large data sets to get the true power of AI. And that's where this toolkit will come into really helping you scale. Where other toolkits you may struggle or spend an awful longer time trying to train the same model on the same data set sizes. Bing uses this toolkit for relevance and ranking. Bing Ads uses the toolkit for recognition of products in advertiser-provided images. So these are used for matching the query to the keywords and different entities that the advertisers want to surface when you are looking for different things in an online advertising framework. CNTK is also used for object recognition. Many of you might have seen Joseph Sirosh's Ignite talk, where he presented in collaboration with Lowe's, a very nice interactive demo where different objects were recognized from the Lowe's catalog and were matched using different features that were extracted from deep learned models in the domain of computer vision. Microsoft Research provides us a great amount of horsepower by developing very cutting edge models and technologies, some of which I will highlight as I go along in my presentation. Okay, I'll start with computer vision tasks because computer vision is one area where deep learning has really made a difference over the past few years. Some of you are new to this domain, so I'll kind of give you a brief idea of what the terminologies in computer vision are. So you typically have tasks around single object as opposed to multiple objects, and within single objects, there's a simple classification task where you want to detect whether the picture has the object of interest. In this case, it's a cat. The next one is whether or not whether the object is present, but where the object is present is also very, very important. So you can have technologies today from deep learned algorithms where you can find different objects within the image. On the multiple objects category, the same thing, but here a picture may have more than one object. In this case, it's a cat, dog, and a duck, and you kind of localize where they are present. And the last one, which is the most compute intensive and is incredibly challenging in terms of vision task, is being able to segment different objects within those multiple object scenarios. And the next generation problems that are coming up are related to video. So you can imagine that if images itself is large, the millions of images that you train on is large enough, how much more compute power you would or one would need to be able to do these very fancy models, which are very, very accurate. It sometimes surpasses human interpretation capabilities on large video images or sequences. So along those lines, how many of you have heard about the ImageNet data? Okay. So for those of you who are not familiar with the ImageNet, it's a challenge for large visual recognition of objects in a huge database of images with a lot of categories in it, and to go along with it, equal number or much larger number of millions of images that go inside the database. Okay, every year people try to meet and beat the performance of their respective algorithms on this data set. Since its inception in 2012, this challenge is called the ILSVRC, and it stands for ImageNet Large Scale Visual Recognition Challenge. You can see that in year 2010-2012, the error rate was about 25%. So lower means better. In 2012, there was a sudden reduction in the error rate by about 10%. And this was largely powered by this network called AlexNet. This is the first time that a deep network came in, and instead of trying to, what was happening here in 2010 and 2011 is people were trying to create the features by themselves, the different features that would be used to do this classification task. In 2012, the deep networks came and automated that part. It automatically recognized the features. It learned those features from the data set. Okay. And later in the tutorial, you will get a chance to see how it is done in terms of working code that you would be able to download from the GitHub site and run it on your own too. But to highlight that since this data set was released, the error rate has constantly come down. In 2015, Microsoft's response to this challenge was the winning one, which brought down the error rate to 3.6. Still continues to be one of the lowest error rates in the domain. This was related to the classification task. If you remember, classification task is given an image, you try to find what type of object is in that image. Not where, but whether the object is present or not. Microsoft had all 5 entries being first places in the year 2015, and it involved not only classification but also localization, detection, and there's another data set called COCO where both detection and segmentation was performed. This high-end algo ResNet will be given to you today as a tutorial. So when I said we'll get down driving the car on the road, I really mean it, because some of the tutorials will cover VGG and the ResNet. Let's see. Some of you may have seen this, that Uber is now adopted Microsoft Cognitive Services for driver identity verification, which aspires to make these rides much easier, safer, and more comfortable and assuring for its customers. How many of you have played around with that how-old.net where you submit an image. And how many of you have seen kids play with it? It's incredible fun to play with that one. You can give it different kinds of pictures and it will guess the age for you. The interesting part I want to bring out here, it's not just detecting where the face is, but it's able to tell rather eerily, being very accurate, what the age of that face would look like. And if you remember, this bot actually illustrates a very key point. When it was initially came out, how many of you initially played around with that bot? And if you play it now, you'll see that its prediction error has significantly gone down. So by playing with the bot, the machine has learned over time what the right age is. So this becomes more of a regression problem, more of a problem where you're predicting a numerical value associated with that picture. So if you haven't played, please go ahead. If you have kids in the house or around that expose them, they have a lot of fun. The next one is a caption bot. This is where the next step lies. And if you notice that this picture is really, really complicated in some sense, and the bot says, I'm not really confident, but I think it's a group of young children sitting next to a child, and they seem kind of neutral. Imagine what the complexity of this task is. First of all, if you notice, it says, I'm not really confident. That means the bot knows how confident it is about the answer it's trying to provide. Secondly, even though many of these children and the heads here are facing backwards, it's able to infer from the few data points that it has what these faces are. And the third thing, if you notice, it's not only is able to detect these are children, but it's also able to kind of give you an idea about their emotions. So the CNTK toolkit does provide you with all these capabilities that you can extract different kinds of information from these images. Now you can think about different scenarios where you would be able to put these kind of applications in place. And trust me, there are quite a few startups cropping up around these use cases. And they might be using smaller data sets to get their prototypical ideas in place. But sooner or later, in order to become viable on a larger data set, they are the people who are going to be using a lot of compute power. And that's where cloud platforms like Azure, with the recently added GPU support, very state-of-the-art GPUs, come handy. And the toolkits like CNTK that we are talking about is fully compatible and performant in those Azure-enabled machines. This is another example where a startup, a relatively new company, it's a German refrigerator company, Liebherr, is partnering together with Microsoft to come up with the next generation refrigerator. Here you can see that we are able to detect the different objects inside the refrigerator. And what would be this? Is this a classification or a detection problem, a localization problem? Anybody in the room want to go for it? Localization problem. Thanks. And along with it, you'll see that there's a measure that you can achieve, because having localized these objects, you can derive different metadata around those. This is a really proud moment for Frank and his team, where Microsoft researchers reached human parity in conversational speech recognition. So if you notice that back in 1993 or so, the error rates were very, very high. In 1995, the error rates were almost like 80% or something like that. So what has happened since then, the error rate has been constantly coming down. And this time, at this time of the, during this time, people were largely using HMM type models, hidden Markov models. So once the deep learning technologies were brought in, you'll see that the conversational speech, which is one of the hardest tasks, the error rate has plummeted, similar to the computer vision. And Microsoft system achieves an error rate of 5.9%. And this is truly enabled because of CNTK's multi-server scalability. To just give you an idea that in order to build these models, you have to train them on a large amount of data, but you also have to iterate to get the right parameters, settings that would achieve that level of performance. So if you were not able to iterate fast enough, it would take you ages to be able to get to these performant models. You may have a fine model, but to get to the right settings, it might take you ages. So in this case, CNTK cut down the time of training to a mere week from months. And consequently, the researchers, Frank and his team, were able to bring it down to a much smaller time frame, and were able to quickly iterate and get this historic moment under their belts. So this is what I'm going to talk now is called AI for customer service. And how many of you have you interacted with this bot that provides Microsoft's customer service? Great. I see a couple of hands online. There might be a few. For those of you who this is new to you, it might sound a bit outlandish, but it's right here at our doorsteps. We are running pilot right now with the Microsoft customer support agent using a bot. This is what the experience would look like. So you would go to this portal, support.microsoft.com, and there'll be an agent for you right there. And you could introduce yourself, talk to the person as if it was a real human being, and it would understand and engage you in an interactive conversation. In this case, it says, can you please, it assumes that, that you have a problem to be solved. That's why you are calling in. So asks you to kind of give you a little bit of details into the problem for which you are calling in. And you have an ability to just type it in natural language. And upon that response of yours, it will go look through the various customer service interactions that it has had, and also look into the corpus online that might be available for you, and surface a set of recipes that might solve your problem. Now, so now the thing is that, think about the complexity of the issue here. You have to detect what the key entities are here in this query from this person. It's about a projector that needs to work with this laptop, and there's a model number given. So it has to recognize all of that. Okay, and then go and figure out from the literature and from previous customer service experience what those problem areas could be, and give you a corrective solution. Now this is called reinforcement learning, because you are interacting, and after a few iterations, you will call it a success. This is different from the previous, where there was a picture of cat, and you said it was a cat, and you kind of tried to predict whether the picture, an unknown picture, would be cat or not. In this case, you are interactively working with the bot. The human is providing guidance. The reward would be when the human being is happy at the end. But until then, it is an interactive process. So it's a combined use of supervised training with a reinforcement learning is what we call. So here, it gave a suggestion, and then it asks that hope it helped. If not, please rephrase your problem. And by rephrasing your problem, sometimes you may elucidate some of these entities. For instance, you will see reviews on online site, right? There's a camera, and said, this camera is spectacularly good. It is better than the Nikon 3000. Now that it refers to that camera that is being sold in the page. It was not very clearly elucidated. So these type of complex mappings of different entities to various language constructs can be automatically learned using deep learning. And then you come back and say, sorry, this didn't fix, I got an error on screen resolution 2. So as you go along, you can see that the bot is able to interact and hone in into a specific area. And then, like the picture, the caption bot, where it was able to say that I'm not really confident, internally also the system knows, the bot knows how confident it is about the answers that it is responding to. And at some point, it may decide that, okay, maybe this is the time to incorporate human intelligence. And you have that option to talk with the real person at that time. So by doing this, what really helps is that you are able to fine tune into an area where the person has problems. You also know which kind of experts would be most relevant in responding to these kind of questions. So this is very, very important because you're optimally able to do these experts, leverage these experts in based on the customer query. Okay. So I won't have time to go into the details, but you probably saw me or heard me talking here about supervised training and reinforcement learning. So there's some nice tutorials. Supervised training, we will do some of them in the tutorial today. There's a nice tutorial on reinforcement learning in our GitHub site. If we have time, I'll introduce them to you. But if not, you can. It's self-guided. You should be able to walk yourself through that. A nice tutorial to get familiar with what I was talking about. And what it involves is selecting a bunch of policies, and it uses internally something called a recurrence neural net, or LSTM, for some of you who may be familiar with. And here in the reinforcement training, you'll see that we use a feed-forward network. And this one is where we collect. This is a little bit unique to reinforcement learning, where you kind of get a way to collect rewards. So what it means is that, say there are n steps to take me from here to that door. And every time I take a step towards it, I get a reward. And every time I take a step away from the door, I get a negative reward per se. And there might be obstacles on the road, so on the way. So I'll go around and find my way. What you are doing by reinforcement learning and this reward mechanism is you are finding the optimal path by exploring different pathways that lead you to that door most efficiently. So in this case, satisfying the caller with the right response that would fix their problem is the end goal. And you may start with certain number of suggestions along the way, but the bot quickly learns what is the most optimal path. It's clear? It's a little bit advanced concept, so I went into a little bit more detail for this one. Okay. Now talking about performance, I would like to bring to you, you have probably played around with a bunch of toolkits out there. So this is a study done by Hong Kong University researchers, where they compared CNTK with Caffe, TensorFlow, and Torch on several well-known models, starting with fully connected layer, AlexNet, ResNet, and LSTMs. What you can see here is that CNTK does very well with fully connected and LSTMs. On ResNet, Torch has a slightly better performance in terms of speed. And however, CNTK is not too far behind. And even otherwise, if you see the other numbers here, you'll see that CNTK does fairly well. Caffe is very much an image processing, a computer vision type of a toolkit. So they do profess in that particular domain about, and AlexNet is one of the initial models that they have pioneered and they have refined on top of it. Even there, you'll see that when we compare to other toolkits, we fare fairly well. This is a slightly older slide, and here you will see that in December 2015, CNTK was one of the first toolkits to support multiple GPUs across multiple machines. At that time, none of these other toolkits would support that. Since then, obviously competition has caught up, and they have added that support. However, we have kept up with the competition, and here is some announcement from NVIDIA where they where they have decided CNTK to be pre-packaged with all their machines. And when they compared the performance of the previous CNTK with the new CNTK v2 on their state-of-the-art machines, you can see that we truly have kept up with the competition. We have been able to increase our performance between CNTK 1.7 and CNTK 2.0. One of the reasons that NVIDIA's has chosen this toolkit to be their default toolkit that comes pre-packaged with all their machines. The next slide I have is, how many of you have heard about TensorFlow? And how do you think that the toolkit favors in terms of performance against CNTK? Is it 50% performant, 100% performant? Means when I say 50%, CNTK being 50% slower, on parity, same as TensorFlow, twice as fast, 10 times faster than TensorFlow. Any takers in the room? Anyone? Any brave soul? 50%? Sounds natural? Why are you guys hesitating? If you have heard about TensorFlow and no one in? I heard somebody. Someone. Go ahead. Don't hold back. All right. This crowd is more on the careful side. In other forums, when I've asked these questions, I've gotten an answer more or less from 200% to 1,000%. All right. I'll give away the answer. Here it is. Take a look at it for yourself. It's roughly about 3 times faster than TensorFlow when it comes to production grade data. And that's where we see a lot of our customers coming in and trying to leverage the computation capability of the toolkit. Now that we have released the v2.0 with the Python bindings, it makes it all the more easier for them to try models and scale them on a large scale production machine. Okay. And what does it mean? That means that if you're spending $3 for a compute, now you'll spend $1 for the same compute. So there was a nice article that came out in eScience Cloud on the new features for the what CNTK 2.0 includes. And there were 2 major changes. And the first one is Python API. And the second one, the author mentions are the documentation and the examples, the tutorials they are in. Please take a look at the content. Yes. Sure. So thanks for the question. For the audience online, the question is there fundamental differences between CNTK and, in this case, TensorFlow, or is it just a technological catch-up on part of Google? A bit of both, but you'll see there are some unique advantages of using CNTK that makes it really faster. And many of it is contributed by from the speech team, Frank included, where you will see that some of his work gives the CNTK a unique edge. And a lot of it is made possible by Microsoft research innovations. Some of the things that I just talked to in terms of the speech historic breakthrough, those kind of milestones really help in making these toolkits very, very performant and gives a unique edge over anything else out there. Yeah, question. So the question is this performance during training time or serving time? Typically, when you are training large amount of, like a production model, you'll train it on, it's the training time that makes the big difference. There is also an aspect of the runtime, but usually neural nets run pretty fast, and depending on your scenario, the requirements can change. But the training time is like, as I said, the speech thing from months to weeks. That's where it makes the difference. All right, good questions, thanks. Frank, do you want to add something? Okay. So I'm nearing towards the the stratospheric view of the toolkit, and I would like many of you to point to this GitHub site of ours. And what that eScience Cloud article was talking about are the tutorials also, which is made really easy for you. You will see at the down here, there's a reinforcement learning tutorial that I was alluding to. So many of the things that I just talked to you, for example, the image hands-on, which we will do later on in the tutorial, talks about the object recognition in the vision domain. We'll do some amount of language understanding, which talks about different entities that we detect and tag them as a part of test data that we have. And there are a bunch of more elementary tutorials that will get you started with as a hand warm-up. Now, if you do like the tutorials and you find it useful, we suggest that you all open up a GitHub account, which is desirable for you to get the new tutorials as you go along. We constantly add the tutorials to this repository. So, and if you ask for a tutorial, you will get it pretty quickly. That's the idea. The reinforcement learning tutorial was asked by somebody, and we provided it within a matter of a couple of weeks. And if you do like it, do create a fork for yourself to play with and give us a star. Now I'll go into the next level of details, which is descending down, not to the ground level quite yet, but from the stratosphere down to where you can actually maybe 1,000 feet or a 5,000 feet view, where you can see the houses. And some of the questions that got asked regarding what differentiates this toolkit, what makes it performant, I'll get into a little bit of that. So just to reiterate, CNTK expresses nearly arbitrarily complex networks by allowing you to assemble simple building blocks to build a complex computational network. And this makes it quite flexible and adaptable for different use cases people are coming up with all the time. The second thing is that it's important to recognize that this toolkit, the solution that you come up with, is going to be production ready. It does achieve state-of-the-art accuracy and efficiency. And if you're not quite convinced with the bar charts and stuff, don't worry about it. Towards the end of my this 5,000 view talk, you probably would be more amenable to the suggestion that indeed, yeah, these things, if somebody did it, indeed it would make it fast. Okay. All right. And the capabilities to scale across multiple GPU and multiple servers. And this is important, that if you notice that the NVIDIA's DGX1 had 8 GPUs in it, and how quickly you are able to scale up. Now imagine multiple servers being put together, as it is in the case of our Azure compute capabilities, where now GPUs are provisioned. You would be able to get similar scale ups with CNTK. Just to give you a bit of a history of this toolkit. The toolkit was created by the speech researchers, Dongyu and Frank being the pioneers in 2012. So it's been there for a while. Okay? It's been refined, new features been added. This was opened in Codeplex in 2015, and on GitHub in January 2016 under a very permissive license. So you can literally use it for whatever you want to do, anyone inside or outside the company. And it's used by Microsoft product groups, and code development is out in the open. And now we are seeing a lot of people outside the company also picking it up. We get constant calls every week with people onboarding or with different kinds of use cases in mind, or they already are onboarded and have very specific detailed questions, like the few questions I got today morning when I woke up. Like, I'm coming to this tutorial and I expect to be these questions to be answered. Okay, for that person. So the question is, are there any plans to support R? Yes, there's no plans. Actually, it's in execution. So our colleagues at Azure have taken up the responsibility to work with us, closely with us, and bring our support to Azure with this toolkit. So we support Docker. In addition to Linux and Windows support, we have Docker. We are moving on to CUDA 8, should be coming out shortly. We have Python and C++ API right now, and yeah, we should add R here too somewhere. Yeah, that would have answered your questions. We are right now in beta, and we C# and .NET on the roadmap. Another question I often get before somebody asks me is Keras support. So that is also in the works. Yes. So that's already in work in progress. Chris, is it? Oh yeah. So the question was that what's the current status of supporting iOS and Androids for runtime? So for those online, we currently have ARM support, and in the next few months, we plan to support iOS and the runtime, the evaluation part, what we call eval or evaluation. You'll see that as I go into the tutorials, you'll get into that part. I can't hear your question, so would you be? So you mean the question is, do we make a distinction on which environment you train on versus which model you want to serve out of? So no, we don't. Short answer. Yep. But the models are models, right? And this is the same code. We don't have different branches to kind of do the for specific platform-based instantiations. Okay. So I'm going to go to the next level and talk a little bit about what does it mean about arbitrarily composing different blocks together using CNTK. Most of you are familiar with machine learning, and so I would assume that you would know this function where you're taking the features X, multiplying using a set of learned weights, adding a bias to it. So this is a linear model. And then you pass it through some nonlinearity, in this case a sigma function, to get the response of that particular unit. So if you are using a linear model, this would be your model. And the first tutorial will be exactly this. Okay. Now the next tutorial that we will get into will allow you to compose this network actually, and we will do it in code. But before you do that, I want you guys to get familiar with the different constructs that we have in CNTK. So what happens is the output of the first layer gets fed into the second layer here, and the final layer is what converts the output of the second layer into a probability, into a range of from 0 to 1 in this case, by mapping it to a softmax function. If these terminologies are coming out across to you a bit strange, I recommend you write it down in a notebook and just look it up, or go to our tutorials. There are links to these different Wikipedias that walk you through these different constructs. Now, once we have mapped the probability, so given a feature set X, you get a mapped probability of what that feature represents. So if it is say you want to have cat, dog, and duck, the output of this feature, and the X is your input image, you would get the likelihood of the image being a duck, a cat, and a dog. Okay, and now you have the actual label y, which says that this picture is indeed a dog. And then this function allows you to calculate the error between your given label and your predicted probabilities. And then you will aggregate the errors and try to optimize it using a learner or an optimizer. So in CNTK, it's as simple as translating this model into code. You can see that this is the times operator in Python 3. And you can see that there's one-to-one correspondence, making it really, really easy for you to convert your concepts into models in CNTK. What does this pictorially represent? It represents these features X being fed into this module here. And these nodes are the operands. And these are the parameters associated with the model that would be learned through this mapping function. So all these objects are functions in CNTK. So what you do is initially I'll go into more details and it will become clearer that you define a template of functions where a function A feeds into function B, B feeds into C, and then you compose them together. And the functions has parameters associated with it. You learn those functions, parameters. Yes? So the question here is the label a binary one or a continuous scale? The predicted label. So the predicted label is a probability, okay? But it will predict whether, even if there's only cat in that image, it will definitely predict what is the likelihood of that picture being a dog, okay? And the labels that the y vector is something called one-hot encoded. What it means is that in your training data set, you probably have cat is labeled as 1, dog is labeled as 2, and duck is labeled as 3. What you will do is you will convert this into a one-hot encoding, which means that you'll have a vector size of 3, where the first element would be 1, 0, 0 for cat, 0, 1, 0 for the dog, and 0, 0, 1 for the duck. So that's how you feed in the data. As you see in the tutorials, it might be going a little bit deeper than at the moment, but I just want to give you the notion of how one-hot encoding works. Predictions are all probabilistic, right? Yeah, precisely. Hopefully in one of the tutorials you'll get to see that too. So here is, in a more formal way, you have the model function, which is here in the red. You have features that map to predictions. This one defines the model structure and parameter initialization. In neural nets, it's very important that you initialize the parameters somewhat intelligently, and there's a lot of research along the lines of how those initializations and what those initializations should be. So pay attention to that initializations closely as you are training your model. There are different kinds of initializers that are provisioned to you in the toolkit, but you can try your own too. Sometimes you can initialize the parameters from another model that has been trained by somebody else, if the network architecture is the same. And by doing that, I'm introducing to this concept of called the transfer learning, where it's a little bit advanced. I'm stepping maybe a bit ahead, but given the context, it makes sense that what you can take is the parameters learned in a different corpus. Say you have trained a language model from English to French, and you learned you had an abundance of data there. You can take that feature set and plump it into another learner for a different language. Or in the case of images, say you have this ImageNet data for which you have plentiful data, okay? And you have learned the models very carefully. you can reuse certain parameters from this learned model to do a classification of, say, whales, or say there was another one called plankton classification, and things like that I've seen, where you can just take the content from a different learned model, lump it as an initializer into your the model that you want to be trained. That way what happens, all the features, the initial features that were learned by the previous model using a larger data set can be transferred into your new learner. And you may not need as much data to get to the refined features which specific to your end use case. The green box here is, we call the criterion function, okay, which takes features and labels, and we measure the training loss. So the loss is the difference between your predicted labels and the labels provided by the by your training data. So the data that where you provide a picture and there's a cat, dog, and a duck label to it, that's the label provided by you or the human or the training data in this case. And you compare it against the prediction of this model, P, and you compute the loss, and you try to minimize the loss. So this defines this particular function defines the training and evaluation criteria, and it computes the gradients with respect to training criteria. Now I said I'm not going to go deep in this part of the lecture, so I won't go into the gradients, but suffice to say, a lot of the models are learned by computing the gradients, or as between steps as you expose different data sets, how you should perturb these weights or the model parameters to achieve a lower rate. And that's achieved by doing something called backpropagation, and it involves computing the gradients between different data sets and over time. These functions are written in CNTK in Python and provisioned through CNTK v2 API. We can do it obviously in other the C++ APIs also, and there's a former approach which is called the brain script, which is also available to you for those of you who are familiar with it, to compute to define all of these. Okay, so the nodes are function primitives and can be composed using reusable composites. Edges are the tensors, are the values that get passed around. So this one would be the weight, this one would be the bias in this case. And these are the gradients which is automatically computed by the engine. And you have something called a deferred computation, which the CNTK engine does it for you. So what it does here is that it can optimize, it knows, say you want to compute the gradients here, which means that you have to pass the gradients from here to these various stages. Once you've computed the gradient here, you don't need to store all the parameters in memory for the previous states, unless you need it, of course, okay? And by doing so, what happens is you can free up memory as it goes along. So you leave the computation, you defer the computation to the engine, and it optimally can allocate memory and reuse memories that are not going to be used. So for the components that you're not going to extract value, it will reuse that particular memory, and you make it a lot more memory efficient in terms of your compute. You don't have to worry about it. The engine automatically does it for you. Yes, please. Yeah, this one, the question is how many layers does this network have? And in this case, it's a very trivial 2-layer network. This would be, I would consider it as two layers and then a softmax layer at the top. Depends what you want to call it. Yeah. Yeah. Sometimes two inputs also called
then it would be called 4 layers.
Yeah,
It's
you want to take. Yeah.
So it's completely confusing. So I recommend to not say how many layers, but how many hidden layers you have. And this one has 2 hidden layers, right? Yeah.
Yeah. Thanks. You can just hang on to it. Thanks. Yeah, there's a wide amount of literature out there that talks about this. So good question. It can be quite confusing. So, and as I mentioned, these parameters can be cloned, which means you can take the network trained using another data set and plump it into your own custom, into your own network that you want to retrain using new data, and they are editable also. And this allows us to build networks of arbitrary complexity, kind of like having different Lego pieces being put together. So we do support a wide range of networks here, feed forward, RNN, LSTMs, convolution. You'll see a whole bunch of these in the toolkit. I won't go into more details of it. Now I'm going to take a little bit of, come down maybe 1,000 feet and walk you through the different stages of the training a model. So we start with the reader, which reads in the data. In part of the reading of the data, you will have to build a deserializer to read the data and feed it into the network that we are going to build. The third point is important, which is automatic randomization. And I'll go into a little bit of details here, like how you want to read the data often requires, it is important that you randomize the sampling of the data and as you feed it into this engine. Because otherwise, often at times there might be correlations in the data. That is, as you have created the data, there might be artificial ways the parameters have been used, or the data might be having some weird correlations. You don't want those. You want the learner to be exposed to random instances of the observations that you have. So automatic, we provide, you can do the randomizations yourselves, but CNTK does provide automatic randomization and distributed reading. And these are important because imagine that you have petabytes of data. How are you going to randomize this data yourself? You can, of course, but you have to do all the work that CNTK already has done for you. So where you can specify where your buffers are and automatically turn on this flag called randomization, it'll do it for you. You feed the data as if you were randomizing it yourself. Those are the places where you can build scalability and ease of computing by leveraging the features of the toolkit. We'll spend a little bit of time with model functions and the criterion functions that I talked about previously. And we'll talk a little bit about packing and padding in one of the specific examples where it makes a lot of sense. Trainer, we support different kinds of training, or learners we call it, based on simple SGD-based approaches, stochastic gradient descent, and also enhancements over it, such as momentum and atom optimizers. So here you can see that there's a bit of code here that talks about that you would import CNTK, you would create a reader, you'll create a model function, you'll create a criterion function, and then what you'll do is train. The train function will take a reader and will take a model. And then you'll train, obviously the model would get trained in, so let me ask you a question. What does this model training mean? What do you get at the end of the training? You get a trained model, what does it mean? In the context of the 2-layer example. You get, yes. So the answer is you get the parameters. In the 2-layer case, what are those parameters? Weights and the bias. So the W vector and the B vector. So you start with some initializing model, whatever you had, you train them, you minimize the loss, you'll get something different from what you started with. And those are your learned models. And then you pass that model along with a reader to evaluate. And this evaluate often is also referred to as testing, if you are familiar with other machine learning terminologies, and where you take the data and expose the model to some previously unforeseen data in the training set. So you get a de novo experience. So imagine taking a test in a school where you have been taught for the whole year on a curriculum. If you are given the same questions, you would probably ace them because you've seen them, you know their answers. But in real life, that's not always the case, right? You get some things that are familiar with, other things that are not. So in this case, you emulate that situation where you give them previously unforeseen data, and then you see how the model does. What is the error rate associated with the model? Now, would the error rate be higher than the trainer or lower? So if you gave the model the same data that it saw in the training versus it didn't see during the training, would the error rate be higher or lower with that test data or the evaluate data? Higher. Our goal is that the difference is not too high. You do expect a certain amount of higher error rate, but it shouldn't be too high. That's the goal. Okay, so in this case, then you define your functions and then you call them in this order. And in this case, the reader, you set it as true, training is true, and in this case, the same reader, you can just pass the value training is false. And you'll see some examples associated with it. So let's see, what does the reader look like? So here you can see that I have something called a mini batch source. How many of you are familiar with stochastic gradient descent? Okay, great. And how many of you are familiar with mini batch sources? Okay, so not as many hands. So let me explain to you. So what happens is, before you get to stochastic gradient descent, you have gradient descent, which means the classical way where you could read all the data, conceivable data, and you train it on that data set. You give all the data instances, you measure its prediction, you compute the error, you accumulate the error, and along with it, you compute the gradients, which means that you compute how these parameters needs to be changed to achieve minimum error on that particular set. Now, it's almost impossible for large models to learn the parameters effectively, especially when you have such a large data sets that you need to be fit in memory that you can compute this in one go. Okay, so the next step of innovation was that you, instead of doing it in the entire data set, you take one data sample. You give one sample, you compute that particular error, you perturb the parameters, move on to the next random sample, and so on and so forth. Now, the problem there is that in the first case, you got a very smooth gradient. That means your loss function would get minimized in a convex optimization problem. It'll be very smooth. But obviously, because of scalability issues and also compute issues, you cannot fit that in memory. So in this case, you switch to one data point, and now it's going to be incredibly noisy, although it would scale, because obviously you could accommodate one data point at a time. Besides that fact, there's also an issue is, are you optimally really using the memory that you have? You may be wasting a lot of memory in there. So in one case, you have a smooth estimate to the ideal gradient that you want to go to. The other one, you have a very noisy one where you do not use the entire memory. So mini batch source is an intermediate ground where you take a small chunk of the data and train the and learn the models from that particular set of data. So this is somewhat smooth. So you should play with this mini batch source example that we have, where you will get to see like how many data sets you want to take as a part of the mini batch. Okay, in this case, I have, let me go to for the online users. In this case, what I'm doing here is this image deserializer takes a map file. We won't get into the details of that, but in the code, you will see this. It effectively maps the images where they are located. And it takes a feature, which is the image in this case, and a set of labels that we already have talked about. And it has these many labels, the num classes. This is a transform parameter. So how many of you are familiar with data augmentation? All right, very few. So what happens is that often the time for these deep learning models, you do not have enough data. Or you may want to train the model to be invariant to certain perturbations in your data sets. So for instance, whether I'm standing here versus I'm standing there, I'm the same person. The trainer should be able to learn that. A human being does it very intuitively. So one of the ways we can do that is by transforming the data. The very simple form of transformation is you take the image and you translate it a bit. Okay. Or you can add a little bit of noise to it. Or you can do a minor bit of rotation. You can do something fancier too. You can take the image and flip it. So I cannot flip myself backward, but if you had a picture of mine, you could flip it. I would be the same person, and you would get exposed to that kind of instance of learning. And by doing so, what you have is say you took all the images. Natural images are very amenable to left to right flips. So you can flip it, and all of a sudden you have doubled your data set. Okay, you add a little bit of jitter, you truncate, you rotate a bit. All of a sudden you have increased your data set significantly. And by doing so, you are able to augment your data, increase your data set, and also make the trainer be more, what we call it, immune to these random perturbations. And as a consequence of that, the generalization error goes down. This is a terminology, you may look it up later, which means that the error on out of sample data set, like what is not seen in training, but out there in the world, if you expose the model to that, it will give you much lesser error by exposing the models to these kind of perturbations. Yeah. So the question is, does that risk overfitting? Actually, it reduces overfitting. The reason is that if you have, say, 10 data points and your model has 10 parameters, so what you would do is you would fit a curve that predicts those 10 points with 0 error. But any out-of-sample error that comes through, out-of-sample observation will lead to a large amount of error because these 10 points will be exactly fit where they are elucidated, but in between it could have wild fluctuations. By doing this random things, you are actually giving the model more data to learn from. And your model may not fit those 10 points exactly, but they'll be close enough, and thus reducing overfitting. Good question, thanks. All right. So here I already talked a lot about the transforms, but here it is where you can see that I'm doing random croppings. So often at times you've probably seen human beings are very good at it. How many times somebody more young than older would take a picture of yours and your head is chopped off, or half of your body is visible. But yet the human brain is able to perceive that object exactly who he or she is. Okay, so why not train the machine with those kind of data sets? So you can do some random croppings. You can, even if your dimensions may change over years, you can learn that by doing some amount of aspect ratio modifications. You can add some noise so that it may be quite foggy, but you still are able to see the person or the object behind the fog, things like that to augment your data. Now, if you were to do this yourself, That would be a lot of effort. Okay, so use CNTK, automated way of doing it, and save yourself some headache debugging these transforms that would otherwise take you some time. So automatic on-the-fly randomization important for large data sets. Readers compose very well, and you can map image to text captions for that bot that I showed. So you could build some very nice data augmentation and read those kind of complex data very easily. So let's go through this. I'll go through this rather quickly so that we can get into the tutorials now. I have a few more slides to go through. So I'm going to introduce you something called the layers library. Yeah. Yeah. So the question is the mini batching specifically designed for the GPU? Frank, you want to go for it?
Compared to what? So one end is you do updates every single sample. If you do that, that's very inefficient, and you simply don't need to do that. So for that, the answer is yes. It is for any architecture where you benefit from caching parameters, for example, and GPUs are very extreme in that case, but also CPU architectures benefit from that. If you go to the other end, is mini batching versus the whole batch. Your whole batch can be billions of samples, right? So there, the purpose of mini batching is that it's simply a waste of time to compute a gradient on a billion samples when you can make a meaningful step forward with 1,000 or 100 samples.
Okay, so so it's not just limited to GPU. It in general helps with the smoothing of the gradients without having to read in the entire data sets when you really can't deal with them in a production setting, because your data sets are going to be terabytes and petabytes. You just can't read them into memory. So the layers library, I'm going to quickly go and talk to you. It's like you have primitives provided in CNTK that are similar to, for those of you who are familiar with it, in Keras style layers. So there was a question in the email, how do you compose those functions? I'll go in a little bit more details as I go into the tutorials. But yeah, we do have function-like composition. So what happens is that in this case, if you see the first layer takes the feature X, it has a bunch of parameters that you need to learn, and it has a nonlinearity. And you feed it into the next layer as your input, and so on and so forth. Now you can really make it, yes? I didn't quite get your question, so. Yeah. Yeah. So you can have different activation functions in the different layers. You don't have to restrict yourself to one. In fact, often at times you'll see that we'll use ReLU for the hidden layers and then use a softmax and the final layer. Okay, so now what we do, okay. So here, this is an interesting construct. So what you'll see here that you have the feature X, and now I have collapsed this whole network into a simple for loop. And this is because we use function composition, you will see that you can have this kind of construct without any problem. Okay, and just to give you an idea that ResNet, that won the image recognition challenge, has 152 layers, as opposed to AlexNet, which has 12. Okay, and a lot of these components have repeated elements. So you'll see later on is how these kind of function constructs really help you to write your models very compact, in a compact way, and in a way that is less error prone, especially if you have deep layers like 152 layers. If you have an error somewhere, it'll take you a lot of time to debug and figure out where things went wrong. So here you would import the layers library, and then there's more and more compact way of representing it. I've provided you in a recipe here so that you can follow along later on as you are going through the tutorials. Here you'll see that we issue a declarative called sequential. That means function f feeds into function g, feeds into function h. The output of this one feeds into this, and the output of function this feeds into this. And here you're passing the feature x into this model. So by doing this, you write it in a very compact way and allows you to compose functions very easily. And there is further compaction in the way the models are written out to make it easier for you. Those of you who are familiar with Keras will find it very, very close to what that library does. I've shown the different transitions here, how you create the models. Now we will talk a little bit about the cross entropy, the error function here, and then you come up with the criterion function and you pass it down to the trainer. The model, the criteria that you want to learn on, and the learner. The learner in this case is going to be either SGD or momentum-based method or Atom. You have a whole bunch of learners that CNTK provides. And our documentation does tell you all the different kinds of layers that are present, starting from the elementary ones, dense and convolution layer, all the way to a more advanced concepts where you can have different kinds of stabilization layers. You'll see a little bit about the dropout layers and recurrent LSTM layers. These are all provided to you through the library. Okay, I was going to do a demo on Azure, but I think for the sake of time, we'll go into the tutorials where you'll get a chance to see what they are. Okay, so to talk about a little bit of how things differentiate, how we differentiate a bit against the other toolkits, I want to talk a little bit about handling of time, which is an important thing for recurrence neural networks. How many of you are familiar with recurrence neural networks? Great. So if you have played around a bit with it, you'll know that dealing with recurrence can be pretty ugly in some of the other toolkits. Okay. Now, hopefully at the end of this few slides, you'll see that it doesn't have to be that ugly. And you can do a much cleaner job without having to spend time figuring out how to build in this recurrence. So in this case, what we have is we start with the same function that we started earlier, a two-layer hidden network, but we are going to feed in the previous value into the current layer. So in addition to the features being fed in, we are going to, and these are previous in terms of time. We are going to feed in the values from the previous time iteration into this network. Okay, and that's how the recurrence thing is. It's forward recurrence. Nothing else changes. In CNTK, it's as simple as writing this statement: past value h1. The engine automatically is able to interpret that, okay, there's recurrence here, and it depends on the past value. So rather trivial question, but I would like to get it, if someone can respond. What would you do if you had to also not only look into, say you want to see New York, you got York, and if you passed in the value new, that would fall into this category, right? Where you're looking into the past or the previous word. Now, if I wanted to capture New York City, what would you do? And you're at York. Your current word is York. What would you like to do? Yeah, go ahead. The answer, past value of past value, in a way, because, well, you are at York, and your previous word was new, and your next word is going to be city. So you not only want to look backwards, but also you want to look forwards. So this one, the backwards was called the past value. The next word is going to be called future value. So you could just add future value to this, and it would take into account the notion of New York City. So this is very important because you want to, if you are going to do location entities, say, New York City is one of the nasty ones, in the sense it's complicated. If you do not have these look aheads and look backs, you can not model them effectively. Yes, please. So the question is whether it's limited to 1 hop back on 1 hop forward. No, it's not. You can do whatever arbitrarily number of look aheads and look backs you want to do. Another question in the back? Okay, great. So we will, yeah, you want to take it?
First of all, you can call past value twice. You could take past value off past value, right? And the second is past value has a parameter that allows you to get to provide an offset. The one thing you cannot do is use a past value and a future value at the same time, right? Because you can only do a recurrence in one direction.
But yeah, good point.
Inside the same loop,
yeah,
right? Yeah.
We'll have an example where we'll do bidirectional lookups. So you'll get to see how we do it. Okay. So here, again, you do this construct, and CNTK will automatically unroll cycles and do a deferred computation, making it very efficiently uncomposable. If you want to look up the corresponding examples in other toolkits, please go ahead and check it out. You would be surprised to see how many extra lines of code you will have to write and to understand even some of those toolkits. For the sake of time, I won't go into that, but if you're interested, I can definitely show you. Okay, this is somebody asked, like, how do you get edge on performance, right? So handling of variable length sequence is very, very important. As you saw that in the customer service call, the length of the tokens are rather different, right? You could ask a very short question, I have a problem with my printer. Or you could say, I have a problem with my printer not connecting to the projector and the model being blah, blah, blah. So all of these were 2 different sequences of different lengths. So what people do typically is they will take a sequence and they allocate a maximum space for it, okay? And then they will stack them up with each of them being one instance, similar to an image with a corresponding label. You will have a sequence with a corresponding label. Now what it means is that this space remains unused, okay? There's no reason that should be. You can just move this to that space and very efficiently make use of the data that's out there. And the hashed out space is the only space that is not used. It's padded data because we could not compose the sequences in more efficient manner. And just by doing these, you can gain a huge improvement in efficiencies. So you can run them in a very much more optimized way. Now the thing is that you can do these things yourself. You can do this thing yourself. Nobody stops you from doing it, but you have to do all the counting, keep track of all the indices, where you moved, how you want to keep track of things. That's not a trivial task for you. It appears, so in CNTK, when you submit a job, you will submit the job like this. Not like this, but like that. You will just send the sequences one at a time, as if you are doing the classical way. Internally, it will take care of all this fancy mapping that yields a huge amount of performance gain. The second one I want to get to is actually the third one. The first one was the implicit handling of time. Second one was the variable length sequence. And the third one is the data parallelism. Yeah. So the question is that how do you handle the delimiters between the sequences when they're packed?
So the answer is correctly. And what do I mean by that? If you, for example, want to perform a left to right recurrence over this, you can see that you can always perform 4 operations in parallel because there are 4 sequences, right? These 4 rows in this structure. So those will be grouped together and launched as a single CUDA launch. And then the next time step for the next 4 will have to be a separate CUDA launch because it depends on the result of the previous operation. Now, as you go across, this function will check whether there are these boundary conditions. And every time you cross a boundary, there will be special handling of this particular row. And internally, it's handled by basically just changing a pointer somewhere. It copies it from somewhere else. And you can, at the moment, also specify the boundary condition either as a constant or as a learnable parameter. And in the future, we'll be able to have a per sequence boundary condition. So then you can very easily implement sequence-to-sequence models, for example, which at the moment is a bit more tricky.
So I'll move on to the next one. I won't have time to go into the details because I really want to spend the remaining time that we have in the tutorials. But before we get to that, one last point which makes it this tutorial really unique is that we have some very innovative ways of doing the optimization steps. And this is unique to CNTK, and the toolkit is all open source except for these 2 optimization techniques that are patented, and for that we require special license if you need to. If you want to run it on Azure platforms, those come to you for because it's Microsoft stuff, it will come to you automatically. All right, so we have data parallelism where we want to distribute the different data sets across different mini batches and then aggregate. That is a given, but the challenge is we run into communication cost. So what I mean by that is that if you want to compute the gradients from the mini batches, say you have a mini batch size of 1024 and about 160 million parameters, you'll quickly see that the compute overhead, the compute time that is needed to calculate the gradients from those mini batches becomes much less than the time it's needed to talk across processes to update the gradients across these multiple processors if you're running it in a distributed environment. Okay, so to the extent that even if you had more than 2 GPUs, even 2 GPUs, you will not be able to parallelize it very effectively because the communication cost dominates. In those situations, what you could do is, you can communicate less each time, and the second approach is you communicate less often. So there's something called one-bit SGD that Frank pioneered here, and it's instead of communicating the full gradients, you actually quantize the gradients to 1 bit per value, but you keep track of the error rates internally and only update them in a very infrequent manner. You can look up the paper for more details. I will not have time to go into that. The other innovation that helps out is automatic mini batch sizing. So you can imagine that you can specify how much data is needed for your optimization yourself, or you can let the system decide based on available memory, your network structure, and your available hardware resources. And the other one is called the block momentum, which is very recent, very effective method of parallelization, and it combines model averaging with some error residual ideas that are captured in that in the paper, if you want to go into more details. Some of the roadmaps, I think we already talked that, C#, Keras, HDFS Spark, and on the technology, so handle models that are too large for GPUs, optimized nested recurrence. NCCL is already in, and then support for ARM and FPGAs. Some of it is already in. I need to just update it. And again, you can go to this GitHub site. You can post the issues in the wikis or send emails to CNTK help, or you can, on the Stack Overflow also, you have the opportunity to respond to questions. So again, To summarize, this toolkit is designed for ease of use, focusing on how, and has a powerful stock library. It's optimized for NVIDIA GPUs and libraries. Best-in-class multi-GPU, multi-server algorithms come to you at no cost, literally. Just download it from the GitHub side. Very flexible, that's the design. If you find areas where we can improve further, please let us know. Supported on both Linux and Windows, and development is completely open. Some of you have been looking into how to reach out to us. This might be a good slide. There is some notebooks at this link that we will use in the next hour or so. My only request is that you can log into this site and create the VMs, but then run them. The reason it's a very shared environment, and with the number of people online and the people in this room, the site may come down to a much slower speed, because the Python is single-threaded, and the way the notebook site is designed, it's assumed that it's single thread, and so that multiple people can use the VMs. However, CNTK is a Python layer on top of a very efficient C++ layer. So the moment you fire something, it will try to grab as much CPU resource it can. So if there are 10 people running on the same environment, it will slow down the system quite a bit. So I recommend that you open the notebook, but just don't run it. Follow me on the screen as I go along and walk you through. You will be able to run those tutorials on your own on that environment. And if you have installed it on your own machine, I highly recommend that you follow along with me on those installed versions. Shall we take a 10-minute break and maybe 9-minute break and resume here at 10:45? And we can get on to our hands-on with the tutorials themselves. Yes. Yes. Hello? All right. Maybe we can get started. Thanks. Thanks, Frank, for hanging around and answering the questions. I really appreciate it. So can I see a show of hands? How many of you have installed CNTK locally? Brilliant. So I'm hoping that you guys can, those of you online also, if you have installed CNTK locally, I would really appreciate if you could run the tutorials on your local machine instead of hitting the Azure Notebook site. Yep. So there's subtle differences of there. The one that is hosted on the Azure side is beta 2, is what I was telling, but you can run the latest version. Yeah, it should be just fine. If you notice that this site is available to anybody in the world, and people can just access it from wherever they want to be. And all you need is a Hotmail, Outlook, or a Live ID to create your own VMs. You don't need to have an Azure account for this. Okay, so I'm going to do the same thing for folks. So I'm going to open the notebooks. You may need to authenticate. This is where you would provide your credentials. And now I have the tutorials running in Azure. At this point, the VMs are getting created for me. And now I have the application running. You can follow along on your notebook if you want to. And I'm not sure how it will scale with the number of users, but it will slow down if too many people get onto it in terms of running it. But loading it should be okay. Okay. So this example is a very basic logistic regression primer, which will walk you through the elements of CNTK to get the simplest of the simple models possible and a foundational building block for CNTK. So you'll see here, it's a made-up example where the red dots correspond to patients who are of certain age and who have a tumor size, a large tumors typically. And somebody has labeled it for you that these are the ones that are malignant and the more dangerous kind. And then there are these blue dots, which are also benign. So what you can see that in general, if you see that as the age increases, the likelihood the same tumor size is more likely to be malignant than the ones for a younger person. And you can learn a separating plane here that would help you classify the malignant diseases from patients with malignant disease from the benign ones. Some of the challenges of a linear classifier here will be in situations like here, you can see that these two blue dots were kind of intermingled with the red ones. However, this is your first model, and for the ones that are more advanced, they will be able to accommodate these other dots as well. However, again, in real life examples, it's unlikely that you will be just going with age and tumor size as your feature. You'll have a lot more features that one can leverage. And that's where the deep models will come in, which automatically learns these features but requires a lot more data also. So the different stages in this building up of your recipe involves data reading, data pre-processing, then we have model creation, and then we'll learn the model, and then finally evaluate it. So if you have followed my the slides carefully in the first half of this tutorial, these should sound intimately familiar. The model here, I'll go into a little bit more details, but it's a very simple linear model. Okay, let me just run. So you can, in the notebooks, you can hit this run cells button and get the ground running. So here I loaded CNTK. And this one, it's an important concept here. So we have talked about the dimensions of the data and the number of classes. In this case, we have age and we have the size of the tumor as our features. So the dimensions of your feature is 2. And we have also made it very simple in this case, because the first one where we are classifying between benign and malignant. So the number of classes is 2 also. Note this logistic regression may sound very simple, but it has been widely used in various production scale systems and continues to do very well in many applications. This recipe that you are seeing here, actually you can replace this number of output classes to 1,000 or 10,000. And this number of input dimensional features, you can increase it to a large number, whatever it might be, 1 million. And the system should be able to scale up to be able to accommodate that. In later examples, you'll see some evidences of that. So I'm going to define the input dimensions and the output classes. And now I'm going to generate some data for you. So here I'm using NumPy. How many of you have heard about NumPy? Great. So CNTK Python API is fully interoperable with NumPy. So you can pass in NumPy arrays if you have data already read in as NumPy. And this example illustrates that. Here I am generating some random data, mimicking that plot that I just showed you. And I'm going to generate 32 samples here. And I'm going to get those features and labels generated here. Here's a bit of a code that will generate the plot, just to make so that I'm able to convince this is really running. You'll see that this plot gets regenerated here. Okay, so reasonably complex data. There's very little linear separation that is possible, but we'll see what the model learns. Here is the model. So you, just like we talked in the slide deck, you have the weight vector, which are the weights connecting from the input features in blue to this green sum, the sum operator, and we add a bias to it. So our goal here is to learn this weight vector and given a feature vector x plus the bias b. The next one is an important concept here. So it's notice that I create an input variable where I'm giving the input dimensions and the data type here. What it created is a container of dimensions equal to 2. I have not put any data into it. It's very simple. It's a container at this point of time. And remember, yeah. So the question is that in this case, you have all the data types to be float. what happens if you have different kinds of data types. Currently, we would convert them into float at the moment, but conceivably, you could try out different data types. Typically, if you have data types, you would know ahead of time what those are. It won't be that an image will have a float in one case. From the same camera, you would get another one that is 16-bit, or something else would be character map. So typically, your data sets of a given feature type will be of a particular type. You could have multiple feature types of different data types. Yeah, but internally, you'll have to map it into something numerical. So you would eventually convert it into a float 32. Yeah. So the question is it a NumPy array, or is it a special kind of NumPy array for CNTK? So you can feed it in a NumPy array, and internally it will reformat the data to the representation that CNTK expects. Because it's a simple array, simple vector is trivial, but you can imagine that different toolkits will have different kinds of formats in which height, width, channels, time is represented. So, and a lot of the recurrent stuff that I talked to you involves dynamic axis. Like ahead of time, you don't know how many elements are there in the sequence. So for which we do some special treatments. So we do internally convert it. But the point is that you could read it through readers that we provide and give the data directly, or give the data that way, which is the recommended way. Or you can, if you have already read the data in NumPy, you can pass it. Okay, so now I'll go into the network setup here. Notice that this is just a linear layout. Okay, and I said I won't show you under the hood what's going on, but I kind of want to give you a feel of what goes on, at least at this level. So I talked about the layers library. So a layers library would abstract these details from you upfront. You don't need to get into that, and we'll see that. But just to give you a flavor underneath what's happening, it's exactly what I discussed in the slide that I showed you. You have weight parameters that you're learning, okay, and the bias parameters that you want to learn. And these are called as parameter variables, okay? And then you do this operation, which must be very familiar to you, which is product of features times the weight plus the bias. And you return the function, okay? I'm creating these variables inside just to illustrate that how you can dig inside the model if you wanted to. Just to give you a confidence that what other toolkits you're able to do, you can do the same thing with CNTK, but we don't expect you to do that. And later on, you'll see that this would be replaced with a one line call to a dense layer, and internally things would happen for you. But if you want to peel apart and go deeper, you're more than welcome to do so. So now I've created my function here, and this is my output. So the linear layer, it's just a simple function. It takes an input of dimensions input dim and an output of output dim. Okay. So now I have the linear function. This is the one of the questions we had, how many layers earlier. So you can see that why we call the number of hidden layers, because in this example, this is the output of the hidden layer Z. In order to convert the learned mapping of this linear function into a probability, we pass it through a softmax function. And then we compute the cross entropy. Here you can see that I'm doing exactly as it was in the slides. Compute the loss, and also we have the label provided by the supervised training data. And then we can evaluate the error against, so between the label and the observed function that we have learned. Here I am setting up the learner. In this case, we are using a simple stochastic gradient descent. You can look up some of the links here on this notebook to go into a little bit more details, and also into our GitHub site, from where you can get into the documentation for the library. And here you can look up the learners, all the different learners that are available. The next thing I'm defining is some convenience plotting functions, which will allow me to see how well the training is going. And then I'm going to, this is the time actually I define my mini batch size. Remember, in the for learning, we feed small batches of data instead of the entire data. So although I could do the entire data in this example, it's not a big deal. It will fit in the memory, but the idea is that you would feed the data with certain bite-sized chunks. I have defined it to be 25, just a random number. People choose all sorts of data sizes depending on how much memory they have. And some of the automatic mini batch sizing is also made available to you in this toolkit. And then you have the number of samples to train, in this case 20,000. Typically, you will make multiple passes through your data sets in your training, which we will see later on with the MNIST example. So here you can see that, and I'm going to run the trainer. Ran pretty fast. It's a simple example. So the model, at this point, the parameters of the models have been learned. And let's see what happens with the losses. So you can see that the loss function that we have, as we are iterating through different mini batches, the loss was rather jumpy initially. Does this make sense? So just keep that in mind. This is stochastic gradient descent. That means even with the mini batch, initially you may wander around a little bit because of the different samples the model is seeing. So there will be noise in the system, but over a period of time, it should converge. Yeah, question. So the question is, how many batches or iterations you need for your model to be trained? So that's a very data-dependent, domain-dependent question, and also depends on the learner. So for instance, in this case, as with SGED, on a complex data set, it might take you many folds longer. So for instance, later on, I'll talk about batch normalization, okay, with some advanced learners called momentum-based learners, where you will see that you can achieve the same amount of training loss or the errors in a much shorter time frame. So it depends on your data set and depends on the learner that you're using. So the only way I would suggest you is that that's where the compute efficiency is really becomes very important, because you need to learn these hyperparameters associated. So the faster you can retrain your system, the better off you are in kind of coming to a model that can do what you want to do on production scale data. Yeah. Question. Yeah. Yeah. The question is that if you have a data size of 100 and your mini batch size is 10, and if you run it 10 times, what is the chances that of seeing the same data point more than once or not? So the thing is that, remember, we are we are asking to randomly sample the data from your data set. When you create this mini batch sizes, we would randomly sample. So it's more than likely that sometimes the data will be seen more than once or not, depending on the random sampling. But that's why we make multiple passes through the data. So if you have a sample of 100, you don't stop with 10 runs of the mini batch size of 10. You may run it 10 times. I have to look into the APIs, but you surely can do it yourself if you want to in the toolkit. Whether it comes out of the box, I have to check. Yeah. Question first in the back, and then I'll come to you. Yeah. Sure. So question is, how do you decide the size of the mini batch? You can leave it to CNTK to decide for you. You can do automatic mini batch sizing, or you can take it in your hands and drive the stick shift car around by moving the gears as you want to. Up to you. It's completely, because some people want to feed the data in a very deterministic way and to be able to gain confidence that it works. So maybe for a small toy example, you may want to do that, but for large examples, and if you want to gain performance, some of the NVIDIA performance you see are largely attributed to the things that we do behind the scenes for you. Yeah.
The model that you converge to, would it be different depending on, for example, the order in which random sampling occurs? If you run the same thing multiple times, you actually see different, or is it like, can you make it different?
So the question is whether the learned model is deterministic or not. The thing is that you can feed the same data in the same order. It will be the same model that you would learn. Whether that's the right thing to do, I'm not sure. Maybe for initial gaining of confidence, and if you really need determinism, that's the way to go about it. But doing it randomly yields you the optimal region where you want to be. And typically the model should not fluctuate too wildly, because then that means your model is flaky. It hasn't seen enough data. That's a good way of checking whether you're between run to run, you are seeing a large amount of variation or not. At that point, it could be that your number of features are fewer, or your model capacity, you may have overtrained, you may need to provide more data. So it's a nuanced answer. I don't have one answer for you. Yeah. So this one, so far, the question is this plot is for the lost on the mini batch training data or not? So this one is on the training data. So we will independently measure on the test data now. Yeah. I think I just answered it a bit ago, which is you can do whatever sampling is desirous for you. I have to double check whether we have that parameter or not, but you surely can set the seed point, the random initializer seed point, so that you generate the same randomizations over and over, or you can provide your own random sample data, right? We will definitely do it with replacement. Without replacement, you have 100 data points and you have only 10 mini batches. You can, with replacement, without replacement, you'll have only 10 epochs. If you have unlimited data, yeah, you can go with that. I think you have to do outside the toolkit, but I have to double check. But you can surely do that without to feed the data without replacement. But anytime you are doing with this, is there a good reason why you want to need that? So the question is that you have huge data. If you did without replacement, you can expose the learner to different data sets. Think about when you have huge data and you have to randomly sample, you have to ensure that that sample hasn't occurred before. Whether you want to spend additional compute time ensuring that, or you just feed it as if you see the cloudy days, the same cloudy day 10 times. You may not be Where do you want to spend your compute cycles? It's up to you. When you have large data sets, how do you want to make it more efficient use of your compute power? So it also depends on the data and the distributions of your data size, data samples. So yeah. All right, we'll go into the evaluation testing. So in this case, what I'm doing for illustrative purposes only is that I'm going to test it on one mini batch. Typically, you would run the test over multiple mini batches and take the average of that as your test error. So it ran the test, and we got certain errors. And now in order to see what those means, I will convert the learned functions output into probability using softmax, and then use this eval function. So somebody in the audience asked me, like, what is the support for runtime on different kinds of devices? It's the eval function that they are referring to, where you have a model that you have learned, and now you want to do the evaluation of that model at runtime. And here you see we are able to detect a few of these, but some of them have been erroneously labeled. And let's see what that learned function looks like. And yeah, in this random instance of data sets, you can see that we did miss a few of these red points. But then it's a very simple linear function. Okay, we'll go to the next one. All right, so this is a feed-forward network, and believe me or not, this is very, very powerful for a lot of applications that you may want to get your hands warmed up with. And here we take the same example with the blue dots from the red dots. Now the difference here is that we are going to learn a nonlinear function that separates these data points. As you can see that in order to get these points correctly, a simple linear separation like we did in the last example isn't adequate. So you want to learn, and real world data is way more nonlinear than this. So as a stepping point, we'd like to introduce you to what we call the feed-forward network model. And here you have the same inputs here, but there's this concept of hidden layers that I had alluded to in my slides. So I'll walk you through that. I'm going to import CNTK. In this case, somebody in the had sent me questions like, how do we set devices? These VMs are running on CPU only. So I've set the set default device as CPU. You could easily just say GPU here and specify the device ID 0, 1, 2, depending on how many GPUs you have. And then the CNTK will appropriately use those GPUs in your training and testing. Yeah. You're seeing the same thing. It's possible that the CUDA drivers that you have installed may not be the ones that are needed. So you have to choose the CUDA drivers that they vary from system to system. So yeah, so we'll have to look into it why that is happening. NVIDIA supported GPUs. Yes, correct. Because we use the CUDA libraries provided by NVIDIA. They do a lot of the heavy lifting. So yes. The question was for the folks online is does the library support any GPU? And the answer is it supports any NVIDIA GPU. We use CUDA libraries provided by the NVIDIA dev team. So next we'll get into the same data generation. So I will just go through it. And here I'll get into the network dimensions, network setting. So in this case, now I have 2 layers. And I have each of the hidden layers, which are these green layers, have 50 nodes. Okay. And now again, I'll create that input variable and the label variable here. These are containers. And here the network, instead of being, in the previous one, it was a weight vector and a bias scalar. In this case, it's going to be a weight matrix and the corresponding biases. Okay. But the code looks eerily similar. If you see here, the linear layer is the similar. These are the elemental blocks, what we learned in the previous tutorial. And then you compose a dense layer out of it. Okay, where we pass the linear layer through a nonlinearity. In this case, somebody asked me about different kinds of nonlinearities that being passed through. So you have ReLU and you have sigmoid, you have tanh. There are a whole bunch of them that is available to you. So I'm going to set up the dense layer. Later on in the tutorials, we will skip all of these and it will become just one layer called dense. Now I'm going to set up the 2-layer connected network. And again, I want to emphasize here, this is where the function composition is happening. So instead of feeding H1, output of H1 to H2, then H2 to H3, you can simply do the function composition using this construct with a simple for loop. So if you had 10 hidden layers, all you need to do is change the number of hidden layers here. Sorry. And you can then define your network here. Yep. Now I have a fully connected classifier. Okay. Linear layer not defined. That means I must have not run it. Okay. So now you get your function is defined. Okay. Now we'll go through the same regimen. And a lot of these things is going to be like boilerplate for you. If you love coding, there is not much for you here. You will just copy paste, unfortunately. I'm really sorry. A lot of if you like feature engineering, again, I'm sorry, the machine does a fabulous job and your job has been taken away. But the part that you really can contribute is how you want to design the network structure, and then what are the parameters that you need to train, what are the different ways you can augment the data, more higher level functions that you would like. And for instance, if you are teaching a classroom, you want the learner to learn how different kinds of experiences you can give to that learner to be able to better emulate what the machine, a human would do. You need to do the same thing to the machine now. This will become more and more apparent as we get into the more advanced tutorials. So now I'm going to configure the training. In this case, we are doing going with a fixed learning rate. This is the first time I'm introducing you to the concept of learning rate, which means that every time I'm compute the gradient, I won't take it as is, but I'm going to scale it to a certain degree so that if I have computed the gradient in the wrong direction, then I would not jump off the cliff by taking that huge step, but rather take smaller steps so that I can not fall off that cliff or go out of control. You can surely play with this parameter, and I highly recommend you to do that. Try some crazy settings. Even if you do, say, 0.5 or closer to 1, you should see yourself falling off the cliff, guaranteed. But give it a try for those of you who are playing around. Okay. Same utility function for plotting. And now I'm going to, again, the same thing. The number minibatch size is 25, number of samples 20,000. And then, I've started the training now. And it trained already. It's pretty fast. And then you can see that I can plot the errors. And you learn the model. And you do the evaluation. I have some recommendations here for you to try out. Try different numbers of hidden layers, try different types of mini batch sizes, try different kinds of learners to get familiar with the toolkit. Okay, the next one, I'm going to kick off this data set. So you can run all of them. Because these are VMs, this needs to download the data onto the machine where these notebooks are running. So while this data gets downloaded from the site, I'm going to walk you through the next tutorial, which is the classic MNIST digit classification data. So this is provided by Jan LeCun's site. These are handwritten digits, and you want to recognize these. And so say each of these images are, say, 30 pixel by 30 pixel wide, and there are 10 digits. What's the dimensionality of the input data? Anyone? These are 28 by 28 images, but if it was 30 by 30, 900, right? And the dimensionality of the output labels, 10. Okay, so the same code that I was using, I'm going to use it here. So here the data set is 28 by 28, so which amounts to 784 pixels. I'm going to feed the pixels directly, and this is the number of outputs 10. And I'm going to read the data from this files that I have downloaded. Let's see if it downloaded. Yeah, okay. Now I'm going to use that same model. Yeah, if it got a bit boring, sorry, again, you just have the lever to play with the network architecture. In this case, it's a same 2-layer network with 2 hidden dimensions, 2 hidden layers, and each having 400 nodes. If you want to make it a little bit more interesting, try one node to be 200, one node to be 400, change the code, see how you can make it going. In this case, I have both the layers to be the same number of dimensions, the hidden number of nodes. And again, I create the input data and the label. There's one thing I should point out. So here in this case, I'm reading there are 2 different data sets, 2 different aspects of the training data. One is the features, which is encoded at features in the data set, and the other one is called labels. So let me see if I can pull out from my local machine here that same data set, so you'd know exactly what is being read. So this is a clone of the repository, so you should be able to do the same things I'm doing locally. So let's open I'll just open the text file, it's just shorter. So what you will see here is that the data set that I'm reading here from the text file is in this format. The first one is called the labels, and the next set delimited by this pipe are the features. So what does this mean? There are 10 digits, and they are 1 hot encoded, right? So this means this is going to be 0, 1, 2, 3, 4, 5, 6, 7. So the corresponding image has the digit 7 in it. Okay. So if you notice in the code now, these are labels and features. So I have mapped labels to the label stream and features to the feature stream. And then I configure this reader, which reads the mini batch source from these two parameters that are provisioned in this reader. Yep. Now, where was I? I was here, I think. All right. So I'll just plow through the same things. Yeah.
So, pardon me if this is a basic question, but how do you decide the dimensionality of each layer?
So the question is, how do you decide the dimensionality of each layer? So you have a job, you trial and error. Yeah, I think there is some room for research here where you can learn a meta learner on top and figure out the science behind the network topology. You can do it brute force. Say you try out different settings, automate this whole loop where you kind of compute the training error and the test error. You take the differences, and for whatever settings you find it to be the least difference becomes your training. You could do that. For simple networks, it would work out. But as you'll see quickly in the next set of tutorials that I'm going to walk in, that it becomes fairly complex. Okay. All right, so the same networks, everything, and here I'm scaling the input to between 0 and 1 because it just gives the optimizers an easier time to find the solution. What did I click? Oh, documentation. The link works. Great. All right, so let's go through it. Again, loss, the same old boring loss, the classification error. In this case, I have a smaller learning rate. And I've passed the loss, the function, the loss, the label error, and the learner to my trainer. This is going to take a tad bit longer to train. So it won't fly by in front of your face. But you can see that between, and by the way, this is running on the Azure Notebook site. So if you guys want to go ahead and give it a try, many of you can give it a shot. You can see that very quickly the error has reduced from a very high number to a much lower number. Okay, should be done pretty quick. Folks online, you may want to try these notebooks also at this point of time. And you can plot the errors. You can see quickly it came down to a very low number. And I ran through the evaluation. Here I'm doing the evaluation across multiple mini batches of the test set also, and you can see that the error is about 1.74. Now, some of the techniques that I have shown you are talked about, like data augmentation, or using different kinds of solvers or something that I'm going to introduce next is convolution, is going to help you detect these things even better, and you can achieve much higher accuracies with this data set. But for the kind of data set we have, and for the kind of network we have on the MNIST data set, this is reasonably good performance. And I'm going to now predict the labels here. And let's see how, and you can see that it does a fairly good job here on this sampled set that I have. And what you can plot it back. And this was a figure 8. So if I choose another number, say whatever, 23, like prime numbers, 2. And there are some of the explorations that you may want to do. So I'm going to next go on to, I have 2 tutorials. These are relatively more advanced. One is based on image recognition. The other one is language tagging of different entities in queries. Can I get a show of hands who would like to do the image one? And the rest of you would prefer the language one? Okay, Okay, all right, I'll start with the language one then. Yeah. So it's possible, depending on the amount of data that you have, your mini batch size data or your network topology, it will use that many resources. These smaller examples don't take that much resource, but trust me, when you get to the image ones, you'll be cranking. Yeah, you'll be cranking for sure. Yeah. Yeah. So there is Ether pipeline that is provisioned for Cosmos data interop, where you can move data back and forth from Cosmos into Philly or CNTK machines. Philly is the cluster where we run a lot of the jobs in a distributed framework using CNTK. Philly. Oh, you please send me an email. I'll send you a link to the link to the. Actually, I'll send it to everybody internally to where the link to the Ether pipeline might be. Okay, and then additionally, we and don't hesitate to make asks for it, because what happened is I was talking about Bing ads being using the image recognizer. So what happened is these images are provided and are encoded in base 64. So base 64 encodings, in order to read them efficiently, we provisioned a reader that would very efficiently read base 64 images and run the training job on CNTK machines. Okay, good question. Yeah. So our question is there any plans to move CNTK into Cosmos? Now, Chris, you want to take the question, or I can give you the. The thing is, CNTK, or not all Cosmos machines have GPUs, and you would gain a lot of scalability by using the GPUs. But
Yeah, so for using CNTK on Cosmos when you don't have GPUs, so again, Sean mentioned that the Cosmos cluster doesn't have GPUs, but if you want to use CPUs, then the TLC team, which Cosmos integrates with, is in the process of integrating CNTK. So you will be able to run CPU CNTK jobs from within Cosmos sometime soon. I don't have the exact date yet, but that work is in progress. And then if you want to run CNTK on GPUs, on a GPU cluster, there's what Sean mentioned, which is called Project Philly, which is an ability to run CNTK jobs on a specialized GPU cluster, special within Microsoft for deep learning.
Yep. All right. All right. So let me switch on to. So this tutorial is also available on the Azure Notebook site, but I will probably choose to run. I should at least run a few on my local machine. So I'm going to close some of these. These are identical tutorials, so I get really confused when, unless I look at the URLs, I cannot make out whether it's running locally or on. So I am in the repository where my tutorials are present. This will spawn the local instance of the Jupyter server. So here, let me download the data first. So what data, we are using a data from a very small data from air traffic controller. It's called the ATIS data. That has variety of information about flights coming in, coming out, cities, different kinds of entities they're in. And we want to tag these different tokens in the text that is present in this ATIS data to the corresponding entities. I'll just explain to you in a bit. So here I'm downloading the data. And here I'm setting the default device to be GPU. Okay. Okay. Some of these tasks are way faster on the GPU. So it would work on those Azure notebooks, but it'll be just quite a bit slower. So that's why I switched over to my local machine, which has the GPU. So here is the data. So first column S0, just like we had features and labels in the MNIST data, you have S0, S1, S2 as your three features provided, three data types provided in your input training. And okay, and what this means, 178:1, it's a one-hot encoding of that token. So you have a vocabulary of your words that is created from the training data, and then you have the 178th word in that vocabulary stands for beginning of sentence. Okay, and that's why you have labeled it as 1. The rest of the tokens are 0. This is called a one-hot encoding. The corresponding label here is O, which means other. Obviously, beginning of sentence, we are not quite interested. But if you wanted to tag it with something else, like my favorite token, then you could just do that. Okay. Similarly, Burbank here is the 272nd word in the vocabulary. And the corresponding token here, 48, indicates that it's beginning from location.city name. That's the tag. That's my classification that I want to put. Okay. St. Louis is the beginning of a two-city name, and Louis is the intermediate I to loc.city name. Okay, so you can have whatever classifications you want to make for these tokens in your training set. We can learn that classification. And then there's a Monday, which is the departure date by day name. So these are some of the labels that we want to learn on. If you notice, the first column is 19. That means if you had the token, the entire query was beginning of sentence, show flights from Burbank to St. Louis on Monday EOS. So this was one instance, one sequence. If you remember in my slides, there were different kinds of sequences. So this would be one sequence. And now you can appreciate the variable length of these sequences because you can express different number of tokens in different sequences. Okay. What we are going to learn is, yeah, sure. So the question is that the format of the data, it's 3 separate labels. And what was the other thing? Yeah, so each row is one instance of that sequence. However, if you notice that, yeah, the S1 we are not going to use. So in your data set, you can have multiple different kinds of features, labels, whatnot. You can pick and choose which one you want to train on. That's A. And the second thing is that even though your internal token, input token, query token might be whatever, it gets converted into this one hot representation. Okay? So question is whether this training data was manually generated. Yes, in this case, yes. Supervised learning, you would like to provide some guidance to the learning learner. You could, if you had a lot of people use a mixed bag of approaches also, where you may have another classifier that generates some tags, but some of them are high confidence, others are not. So depending on your appetite for labeling, there are different kinds of hybrid approaches that you can take to generate the data. But in this case, yes, the data set provided had labels. Okay, so what we are going to learn here is these embeddings. So maybe at this point, switching over to a slide may not be a bad thing. Okay, so I think I explained to you this a little bit in more details than this slide does, but it will help you reformulate some of your ideas and connect the two. All right, come on. Okay, so what we want to learn is an embedding where we take the tokens from here and we classify them into these different entities. Yep. And in this case, beginning of sentence feeds into it being an other. Now what we want to do, and this is where the recurrence comes in, is that the next word can really learn from what its previous word was. And that's why you pass in the learning between the layers. So the fact that word from occurred before Burbank means this is a departure city. The system automatically learns that. Okay. So in CNTK, you would have very simple representation of your network. In this case, we have an embedding. Embedding is nothing but taking these vocabulary words and representing them in the form of a vector, in a rich vector, so that two words that mean the same thing will be closer together in a vectorial space. Okay, there's a lot more to it. I can go just talk about embeddings for a half hour, but for the sake of this tutorial, I'm representing this network in a very concise way. You can go and dig into deeply into each one of these. Have you heard about word-to-vec? Many of you may have word-to-vector embeddings. There is sentence-to-vector. There's all sorts of vectorizations possible. So what you mean, you take a word and embed into a high-dimensional space. Similarly, for images, you will see that you can embed a big image into a vector space. So that would be called image-to-vec. So you will have, these are called embeddings. Yeah. So the question is that there's an assumption that there's no sentence more than 300 words long. No, not at all. In fact, it represents the dimensionality of the network inside that memory cell, how big that network is. Think about when we generated that feed-forward network, right? It had 400 hidden layers once we had 50, right? That's that number. It's nothing to do with the number of sentences, number of the length of the sentence. In fact, if you see here, the length of the sentence can be really, really long here. It could be whatever, okay? And the recurrence system will take care of that, okay? So in this case, you have an embedding of dimensions of 150, and the the hidden dimensions of the recurrent cell is 300, and then you project it into a flat dense layer equal to the number of labels. No, the vocabulary here is, the question was whether the 150 means it's 150 word vocabulary or not. The vocabulary in this case is 69. Okay, and you can see the dimensions into it. 150 is an embedding. That means you project these 69 words into a latent dimension, into a dimension that you learn. So these embeddings are learned vectors. These are not provided vectors. Yeah. So similarly, an image, you could take an image of, say, 1K by 1K, that would be 1 million pixel, and you will reduce and project it into a dimension of, say, 1K, just 1K vector. So it can be reversed. Yeah, you can have all sorts of. It could be. You can play around with these dimensionalities also, and and you can interpret the data depending on what you see the results to be. Yeah, question. So we you can do it, the stop word removals using when we do in the reader itself, if you want to. And what you can do is in the one hot encoding, you can put them into an other bucket also. You can do whatever kind of you choose to do so. Yeah. All right, back to our tutorial. So you can see there's a one-to-one correlation here. So now here you can see that the number of labels, sorry, the vocabulary size is, I got it wrong. Sorry, I really apologize. 69 is for another data set that we have. This one has a 943 words in it. And the number of labels here is 129. And the number of intents, which we are not using here, is 26. And the embedding dimension is 150, which we talked about. So yeah, you are going from a higher dimensional vocabulary to a lower one, but you could go the other way around too and see what happens. A hidden dimension is 300 here, and what you're doing here is that you are generating this function. So this should be pretty, I would like you guys to really understand this part. There's a function called embedding fx that feeds, output of that would feed into another function called recurrence gx, and that output of that function goes into dense, which is hx. So you have a function composition which is f of g of x is the parameter for, so f of x is a parameter of g of x, and that composite function is a function of h of x. And the output is h, g, f, all feeding into one another. And this is achieved with this sequential declaration, making it really compact. If you're familiar with Keras, these kind of structures will be quite familiar to you. You can pass in different kinds of initial states and stuff that makes it really, really compact to write code. So now I'm going to take a look at the model. Okay. So I printed, so there are, in this case, we have 3 model layers, right? One for each. And then I print the embedding layer's shape. And this is -1, 150. So what does this -1 mean? The -1 here indicates that we don't know what the input dimensions are yet, because I have not fed it any data. I have just constructed the network. Okay. When I give the data to this template, so I've defined a template container. I just defined that function f of g of h of x. That x I have not told what it is. And so this is a template that you are defining. And now what we'll do is you'll feed in data into this container. And as you fill the data into this container, the model dimensions will be whatever that data dimension is. So that's why you can see the model dimension being -1 and 150 is the dimensions of the embedding. It's a key concept, so it's important that you recognize this. Yeah. So question is whether we are using whether we are learning the embeddings here or we are feeding in pre-trained data from other embeddings. So you can do both. In this case, we are learning it. Yeah. Okay. And then the next layer, which is the model 2 layer, this one is pretty well defined because this is the dense layer. We know the number of output labels, and we know the output of this recurrence dimension. So, and it's initialized to this 0 state. So you can print that out. Did I run it? Okay. Okay. All right. So now let's see the reader. So the reader here is very straightforward extension of what I've shown before, but I think it will help to reiterate a few things. The first one is we define a query stream. Intent unused, we are not using that. Remember, S1, we are not using anything. And then the label streams, so we call it the slot labels. We are saying that you randomize the data here, and we are going to infinitely repeat the sampling. We call the epoch, the whole data set size that we go through. And if it is training, else full data sweep. Full data sweep means one sweep. Somebody was asking, right, if you have a set of 100 data points and a mini batch size of 10. So one full sweep means going through all the data points once. And infinitely repeat means you'll sample again and again, randomly. And that's important for you to be able to get to a great, what you call, you give the trainer the view onto all the different permutations in which the data can be observed. So I'm reading some of the, like what are the different stream keys, and you can see that it's intent unused, query, and slot labels, nothing new here. And now here I'm creating a function. The labels I have not given it yet, but I'm creating a placeholder entity for that label. So you can have a placeholder hold your place before you know what is available to you. This is an important concept. And later on, when you know at the time of training, you can replace that placeholder with real data. Now I'm going to talk to you about a few things here. So here I'm going to now replace these placeholders with the vocabulary size and the number of input labels. Okay. The size is the data set size is about 36,000 in this case. So we are setting the epoch size to be 18,000. You can set whatever. Mini batch size I'm setting it 70. And here it's interesting here. So you'll see that the learning rate, previously we are using a constant. Now we are putting a schedule. What it means is that in the first 4 iterations, we are going to use a learning rate of 0.003. And as the training progresses, that means initially we are going to take long steps, relatively long steps. But as the training progresses, I'm going to reduce that step size so that I can hone in into the region of interest and lead to convergence. The initial learning rate is big so that it allows you to explore. Now I'm sure I'm going to get this question if I don't answer, is that yes, you have to iterate and learn the parameters yourself. Automatic learning rates are difficult to achieve. And there are many literatures. It depends on the size of the data, the solver that you have, and the kind of optimizations you want to run it on. Now there's a concept of per sample, and per mini batch. So per sample means each data point that you are sending through can perturb the weights and the biases in a certain way, certain amount. Now, as you iterate through a lot of these, you will be accumulating those contributions. And in a mini batch setting, what you would do is you'll do the aggregation of the samples, aggregation of the samples, each sample's contribution to this learning rate. So typically, mini batch learning rates are larger than the individual sampling rates. Okay, so here you will say that you are going to be multiplying the learning rates by the mini batch size. This is important to understand because a lot of the toolkits, other toolkits, use mini batch sizes based learning rates. And when you have fixed mini batch sizes, there's no difference between learning rates per sample or learning rate per mini batch. Okay. However, because we do all sorts of optimizations behind the scenes, we can vastly take advantage of those parallelizations internally if we do things in a per sample mini batch settings. So internally we use the learning rate per sample because it gives a much more tighter control over the number of sequences what you have. It's a little bit advanced concept, but some of you are there. So if it doesn't make sense to some of you, don't worry about it. Just carry on with the basic, simple learning rate concepts that you already have. In this case, I'm using Atom as the optimizer, and let me start the execution of it. It's going to take some time. So here what I'm doing is I'm running it through quite a few number of iterations, and you can see that it takes about 5 seconds per epoch, and there are about 60 samples that I'm going to 16 epochs that I'm going to run through, and you can see that the error rate is already coming down. Now the next step for this model is to run the evaluation, and here you can see that the results of the evaluation here. Okay, I've pre-computed this for the sake of time, but here I would like to have, once it finishes, I will show you, we can play around with a little bit of the data and show you how to muck around with the evaluate function as soon as it finishes. So while the training gets completed, you can see that the evaluate function actually given a random sequence here, like Boston flights from New York to Seattle, it's able to tag the corresponding entities with the corresponding tags. So times is the flight time, then Boston is the to location city. And here is the illustration of the function composition that I was talking about, FGH. You can go through it separately and convince yourself that this indeed is doing the same thing. Now there's a technique called batch normalization, which is a little bit advanced optimization, and another technique that somebody asked me, like how to know when to stop, how many iterations. Batch normalization often works very well, and you can really compress your training times. I won't go into the details, but in this case, you can see that the test error rate is roughly 2.2, and the training error rate came down to 0.3. Let's see if this is completed now. Almost there. So this one, the training error rate was slightly higher, and let's see how much was the test error rate. So the test error rate was 2.7. So by doing batch normalization, I've been able to knock it down a little bit. Then I can do something called a look ahead. So instead of just looking backwards, I can do look into the future value of the state. So instead of saying go backwards as true, I turn it as go backwards false, and then I add a look ahead, one word look ahead. And you can do multi-word look ahead too. Just change this function here. And by doing so, you can see that my didn't make much of a difference between the batch normalization and this one. The error rate there was about 2.2. Here it was 2.3. And then I told you I'll give you an example of the bidirectional recurrence. So bidirectional recurrence involves an entity being called birecurrence, where you are providing both forward and backward information into the network. And if you do that, your error rate comes down a tad bit, 2.1. Okay, so let's do the evaluation part now before I go to the image one. So let's run it. And here I got the entities to be New York. New York was beginning from city. York is I, 2. So now if I put, say, New York City, what should city be? So city turned out to be an intermediate from location. So you can do different kinds of evaluation. So this truly exemplifies that you can pass in whatever data you want to for the eval. The other thing you can also, it shows that you can pass it a NumPy array of one hot encoded vectors to directly run the evaluation. So if there aren't any questions, I'm going to go quickly switch to the convolution neural nets with the image hands-on. Yeah. So time series, yeah, you can use it for that. We have a couple of examples coming up for time series. It's in the works. So you will get to see it on the GitHub site. And yeah, you could use them for time series also, yes. But you'll be amazed how much convolutional neural nets can achieve. There's some latest literature coming up that convolutional neural nets can perform really well. Okay, and LSTMs might be a bit of an overkill, but the jury is out. Okay, so here, this is an image classification task, and we are using a relatively small data set called the SciFar10 data set, and you have 10 categories here, okay? And you have a whole bunch of images of airplanes, automobiles, bird, cat, dog, whatever, okay? So the convolutional neural net is, for those of you who are familiar with image processing, the designing these kernels used to be a big task where you would learn how to extract features of these data representing the different kinds of gradients in the image, different kinds of edges, different kinds of corners and whatnot. Deep learning just took that away completely. So you just feed the data, you define the network, the system automatically learns these kernels and thus is able to capture the features from the data itself. And this is way better than what predefined different set of kernels were achieving. So so typically convolution networks will have, they'll take the image and then they'll generate these things called the feature maps. And these are generated using some convolution. I'm going to talk about these operations just in a bit. And then you would do some kind of a reduction of information using subsampling, or you'll hear this word called max pooling in a bit. And you repeat these steps a few times, and there are some tricks along the way to that you can do, and it will convert these feature maps into a larger number of feature maps. But the image sizes, the feature maps themselves reduce, but the number of features keeps growing. So that's what is meant here. You start with 5 or whatever, 4 here, then it quickly becomes much more than 4. And then finally you embed it into a dense layer. And this layer, if you want to do classification, will, in this case, there are 10 categories, so there are going to be 10 outputs. The dimensionality of the output layer would be 10. Let's talk a little bit of the convolution for those of you who are not familiar. This is the kernel that needs to be learned from the data. What it does is that you take the flip the kernel and do a matrix element by element multiplication. If you do that for this red box with this kernel, you'll see that you get a value of 10. You slide it by a certain amount, say 2, in which this case becomes the green box, and you get the value of 14. So this becomes the output of the feature map. So in this example, these arrows, this kernel is the arrow, the convolution operand that is learned, and the feature map is this value that was generated here. Okay, then you would learn one kernel for one output channel. So in this case, there will be 4 kernels that would be learned from the data. Okay, so you will have and you stack them up. So your input image was whatever x dimension, x and y, or h and w in height and width, but now you have generated, say, depth number of kernels as the first step. Here it's very trivial extension of that concept. You kind of define what the shape of the kernel is and the number of filters. Then you define an activation function, which is the nonlinearity associated with it. In this case, it could be ReLU, sigmoid, tanh, whatever. Certain things work out better than the other. You have to do some initialization. You can pad the images because there's some boundary condition stuff that needs to be taken care of if you want or not. And then there's strides, which I described to you, like how many times this things moves between, say, in this case, the red box moved to the green place and it had a stride of 2. Max pooling is really, really simple, actually. So if you have a 3x3 or a 2x2 neighborhood, in this case, it's a 2x2 neighborhood, you can take this this orangish region and just take the max value out of it. Okay, and this leads to reduction of the size of your features. Then there's this concept called the dropout. So dropout means you will take the output from these different layers that are coming and randomly ignore them. All right, with a certain probability. So in this case, you would, with a dropout rate of 0.5, you'll drop half the activations. You'll just ignore them. This is really, really important because it leads to reduction in overfitting. It has it improves, regularize the output for those of you who are familiar with the ML terminologies, and it also generalizes the solution better. And then batch normalization is rather involved, but what you do is you do some transformation on the input where you normalize the input batches with their corresponding means and variances. There's some nice convergence property that it leads to. So now let's see how it looks like in terms of training these CIFAR images. So here you have a image, RGB image, which is 32 by 32 by 3 channels for the RGB. And you will learn one kernel, which is going to be 5 by 5 by 3 that will map into this space of features. So one kernel, one slice in this block. So it will be 32 by 32 blocks, and then you will learn 32 of these. So in many cases, and that's a parameter for you to play with. You can define however many you want. And these kernels are 5 by 5. So you can, one kernel per slice in this particular diagram. And as you go along, you can then do something called a max pooling, which I just described to you, reduce the size of the image by half, almost half in this case, because we use the 2 by 2 max pooling. And then you can, actually 3 by 3 max pooling. This picture shows 2 by 2 max pooling, but the code has a 3 by 3 max pooling. And then you do the same thing, and finally you embed it into this one vector. So if you think of this image and this vector, this dense layer, that's an embedding of an image into a vector. And then you have the final 10 layers of the different categories that you want to learn. Yeah. Not a whole lot. The question is whether grayscaling the image would help. Actually, it might hurt because you have different complementary information in the color channel. So you do want to preserve those. If you grayscale them, you might lose that thing. Yeah, I mean, the image things requires a lot of compute, and that's where the scalability of CNTK really shines. Reducing the number of dimensions from the 3 to 1 doesn't make much of a dent. I think it hurts more. So if you look at the basic model here, again, following the layers concept, and this is where the layers concept really, really makes a difference. Here you would take the convolution layer, which is a 5 by 5 kernel, and you are going to generate 32 maps out of it, 32 different kernels you're going to learn. We are going to use something called a GLORA uniform initializer, and the activation is value, and we are going to pad the data. This is the input. Then the output of this goes into the next layer, and so on and so forth. You can train the reader. In this case, the image is 32 by 32, number of channels 3, and the number of classes are 10. Okay. And if you're wondering why I'm not clicking on this, it's just that this network, it's not that this network won't run, except you'll kill me for having eaten up your lunchtime. Even on a GPU-enabled machine, it would take some time to run these cells. But I'm going to walk you through, and these are, I think I do have pre-computed data for having this run this notebook before. Again, the same old boring training and testing framework, except this part will make your life really interesting. You would iterate and try out different parameters, and you'll strive to hit the jackpot in the first run. Unlikely you'll hit it. You'll probably this will keep you busy. This particular learning rates, how you want to mess around with it, and trying out different kinds of learners. In this case, we are using a momentum SGD. I've shown you SGD, I've shown you Atom, now it's momentum SGD. So try out these different algorithms that are the learners that are available. And then you do the same thing. It's a little bit more code, but it's the same old thing that we were doing it for the basic reader, a basic feed-forward network classifier. And then you would do the plotting. And here I have just trained it on 5 epochs, which is tiny. So which means 5 passes through the data, right? And you can see from 73%, the error rate came down to 47%. And each run on this data set took about 20 seconds, roughly. This is on a GPU. So if you want to, with 47% error, it's slightly better than a coin toss. So you can't really rely on it. But if you let the trainer go for a long period, it will come down significantly, okay? So queue up these tasks as you go along, because it might take a while for you to get to to a pretty decent learning rate. But you can get an idea that it's starting to come down in a very desirable way. Now I'm going to show you that big hunk of a code that you had here to define your models. You really need to use these constructs that I had talked about in this sequential constructs and layers and stacks of layers for image-related tasks because the networks become very, very deep. Not necessarily more complex, but more deep for sure. So in this case, if you see that just by doing this lambda expression, I'm able to create 3 sets of convolution and max pooling with different parameters passed in. And I could pass in the nonlinearity also along with it. And if you notice that if you run longer, I just wanted to give you a feel that it would achieve a smaller error rate. You need to run it a lot longer. But the same model that was instantiated above, you can write in a much more compact way here, and you can achieve the same error rates as before. Now this one, somebody asked me about the probability, I think you just left, that what is the output of the network, and here I'm just taking this truck image, and you can see that the prediction comes up with whatever it is supposed to be, which is a truck with 72.66, but it also says it looks like a cat, which is, you know, if you stretch your imagination, maybe it has the eyes, whiskers, I don't know. I don't know about the dog part though, but it's very small. You can see that, you get an idea that it is a continuous representation of a probabilistic representation in this case. So you get that. Now I'm going to go into some more advanced concepts, which I talked about before, which is dropout. So you can add a dropout layer, which means you're going to ignore certain activations that come out of this different layers. And in this case, I'm going to drop out at the rate of a quarter. And you can see that my error rates actually didn't go down much. It was 47 before, roughly at the, yeah, it was about 50.2, and here it's 54. So the dropout didn't help much. So this is where you will tweak the parameters. And then here you can see that I am playing with batch normalization. So I've added batch normalization and got rid of the dropout. And by doing so, you can see that how significantly the error rate has improved here. So that's primarily your responsibility as a deep learning specialist to come up with this different combinations of these network topologies that yield the best functionality. Now I'm going to talk to you about this VGG9. VGG18 was the one that won ISL VRC. This is a VGG9, but it's so trivial to code. You can imagine now, this is all that you need to win that challenge of that year, 2014, I think, or 13, I don't remember exactly, when VGG won the ImageNet challenge. Now you can appreciate why this layer stack concepts become very, very important. In a very compact way, you are representing 3 convolutions here, 3 convolutions again, and a max pooling. And you're repeating it to emulate this structure. If that's not enough, the residual network ResNet, which was the winner of 2015, which had 152 layers. I can't draw this, it will take pages away. But it has a lot of repeating entities here. You could, and which corresponding to these, the ResNet node and the residual node increment node. And you can code it pretty much here. You code the basic elements, which is convolution with batch normalization. And the ResNet basic model uses a interlaces the convolution batch normalization layer, convolution with batch normalization. And then you have the incremental layer also reflecting this network. You can read up the paper or go through this code maybe after this tutorial and convince yourself that's indeed what's doing. And this becomes your overall network. Okay, and you could decide now number of stacks you want to stack up. So that really makes this very advanced networks very simple and less error prone. And you can see that these networks have larger number of parameters to tune, so you have to run them for a much larger number of iterations. For sake of time, I've just stopped it at 5 to give you a sense that it does take a lot of time. Initially, you saw that the first network was getting trained at about 20 seconds. This one is up to 80 seconds now. So it does take time, and that's where you will gain efficiencies from the optimizations that I talked about earlier with CNTK. So if you were to use a slower network, slower toolkit or something, you might take you, like instead of 80 seconds, it might take you 240 seconds, which adds up. And if you have to do it like hundreds of times, you just add up those minutes. You'll easily do the back of the envelope calculation. You'll see how quickly you can turn around these models with different parameters that you need to try out. You add a remove a dropout, you'll have to retrain the whole thing to see how it did. You change another parameter, you have to do it again. So all those things matter. All right, I think that's about it. I would like to stop here. There are a few more tutorials that are on the GitHub site. On our GitHub site, let me open it up once again. So you can go here. And there are a few more tutorials like sequence to sequence and the reinforcement learning that I didn't get a chance to cover. You can try them out and learn some of these advanced concepts. That's about it. I'll take questions. I'm here for a bit. Do we have questions online? All right. It's on my, okay. Just give me a second. Okay. 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 My data is small. Distributed reading is not. This is not a problem. Yes, I know I can provide chunks of arrays to the mini batch training, but I do not know how to deal with recurrent nets, how to tell LSTM that first 5 rows belongs to sequence 1. Okay, so when you go through the tutorial again, you will see that there was, at the very beginning, you have the column which says 19, which means it's the 19th sequence, and all the data points belonging to it are clubbed under that 19 row. So here, so if you have 19, this is the sequence number 19, and the data formatter would have converted into this format. So you would kind of provide it would automatically take care of your variable length sequence. Regarding your mini batch, and because your data set is small, you could either use the text reader or you could convert it into a NumPy array, just I've shown like I have done it here in the code here in the evaluation part. You could just convert it into a one-hot representation like using the code here. Okay, let's see what's the next question. Are there any questions in the room before I'll go back and forth? Okay. Yeah, you guys have been asking me question all along, so that's great. Yeah, hide the Python somewhere for future reference. It's already available in GitHub, so it's there for you. And the last one, the variable length sequence packing and padding is done for both CPU and GPU. As I said, that assume that it's running on data science VM in Louis Cognitive Service is using CNTK. The cognitive service, as I mentioned, does use it. And for the first question on the CNTK installation on the data science VM, yes, those optimizations are done behind the scenes for you whenever possible. All right. Yeah. Okay. So I'm going to briefly talk about that, and maybe we can take it offline afterwards because I'm sure people have other things to go to. But let me say, where did we see learning rate schedule? Okay. So if you notice here, the initial learning rates are higher, and subsequent learning rates are smaller. Okay. That means first, initially, I'm taking a larger step, and subsequently, I'm doing smaller step. Now, in a lot of other toolkits, you will see that learning rate is specified as a mini batch, and it's constant. Okay, it's a constant thing. However, if you notice that if you have a sequence which was heavily packed, say you have 10 sequence, okay, that got packed into say 2 spots, your mini batch size now will become much smaller, the virtual mini batch size, because we have packed it up, right? Which you don't want, because if you had 10 samples versus 2 samples, the weight should be somewhat different. So that's where the per sample per mini batch comes into picture. And here, if you notice that we scale up the per sample rate to per mini batch. Okay, but you can pass the mini batch size too. If you're like in images, typically your image sizes don't change that much. So you can just specify per mini batch, and internally you will scale it down to per sample. Typically per sample rates are smaller than per mini batch. All right, thank you guys. Thanks for being here.